Hello. Okay guys, so when Leo asked me to introduce the journal club, I assumed I'd just be able to do the normal thing, which is just go on Facebook and get the stupid pictures of Leo and then show them to you guys and you will laugh and it'll be easy. But it turns out Leo hasn't really got any photos on Facebook. He's got one profile picture and it's just the anonymous logo, which is kind of awkward this sort of process. So I decided instead, what I do is I just make my own picture of Leo. Yeah. This is Leo. So, one of the most distinctive things about Leo, which you guys all recognize him for, is his cool and amazing haircut. So I'm going to put that down first. Isn't that pretty? Now, the lesson known thing about Leo is that under his sleeves, he's actually got a very muscly arm. You can see here. But it's only on his right arm, because of all the petting he does. After his physical attributes, there are other distinctive things about Leo. Most notably, of course, is his fabulous and glorious eye pants. And they're gorgeous. But also, Leo's got very strong political opinions, and he likes to make sure everyone knows about these political opinions. So he'll shout them loud and proud, and it's represented with a t-shirt. But that's not the whole story of Leo. He's got more to him than that. Leo is also very musical, and this is represented here by the classic piece of French heritage, didgeridoo, which Leo plays excellently, but that's not actually the best instrument that Leo is good at. Some of the most beautiful sounds I've ever heard come from sitting in a classroom with Leo, and just listening to him. He's playing a laptop. So I'd like to just finish with, this is a picture of Leo, but Leo is more than just his image, and it's what he says that is the most interesting thing about him. And I just want to leave you with a classic phrase that Leo gives. This is often a phrase he gives when he's in an argument with someone about how much he loves capitalism, and they're making a really good point, and he's thinking, oh crap, that's right, oh dear. So he just says this. And everything is fine.
Thank you, Finn. So, today I'm gonna talk about an old dilemma, the needle in the haystack dilemma. So, the needle in the haystack dilemma is a very old idiom where you have to find a needle and a stack of hay. And this is a really, really hard job because the needle is very tiny and hay is very numerous. So when you look at the needle and all of the straws of hay, how are you going to find it, right? So now I want you to imagine you're a molecule and you're in a nucleus, right? And around you is a lot of DNA, about 3 meters for a human cell. So if you're a transcription factor, you measure about 10 nanometers. Now, if I were to rescale that 3 meters of DNA to your scale of life, that is like a human body of about 1 meter and 70 centimeters, that 3 meters of DNA will look like a string, which is the distance from the Earth to the Moon and back, right? So that's a long string. And your job as a transcription factor is to find a 1 meter tiny piece on that string and bind to it very specifically, right? So in 1970, Riggs and his team were studying the lac repressor binding on the lac operant, right? And they made a finding which startled them, was that the lac repressor finds the lac operant 100 times faster than what is theoretically available for a 3D diffusion process, right? Like it is 100 times faster than what the theory will even predict as the maximum value it can go to. And it's 1,000 times faster if you actually look at protein-protein interaction speed and how they bind. So the question became, how does the transcription factor find its target so efficiently? And so the Riggs basically proposed a model that he called the 1D, 3D search model. And in that model, it's a very simplistic model where you basically just, diffuse in 3D, you're in the nucleus and you're a transcription factor, you diffuse there, and you have a probability to bind non-specifically to the DNA and to slide on. And when you bind to the DNA and you slide on it, it becomes a one-dimensional diffusion, right? Because you only have a string and you can only diffuse it right or left, but you're still bound to it. And what that does, effectively speaking, is that it reduces the dimensionality of your search. So instead of having to search in a 3D space now, you have to search in a lower than 3D space. And because of that, speed at which the transcription factor finds its target now becomes theoretically possible, right? But this is still a very simplified model of what the nucleus and the search process look like, and there's still a lot of open questions. For example, at the molecular level, does the DNA sequence influences the 1D search? Or the protein conformation, like when it changes, does it allow locking mechanism on the target sequences or facilitated 1D sliding where it will just, encompass the DNA? Or some special effects, like what's the dynamic, right? How does the transcription factor slide? Does it jump often? How many base pairs does it look like? How long before it jumps back into a 3D fusion? Those questions have been sort of studied, but are still very open questions, and we don't really know the answer to them. And finally, the nuclear geometry and cellular crowding, which is how does the search proceed in a cell, which is a very, very crowded environment, right? You have molecules all around your cell. You have big chunks of DNA. You have chromatin. Does the chromatin formation changes the diffusion? Does the nuclear domain or the chromosomal domain changes the diffusion? Because all of that geometry in space around you will influence where you can go and where you cannot go, right? And for the next part of this talk, I'm going to basically focus on the nuclear geometry and the cellular crowding. And first, I would like to introduce you to sensing geometry. So I made tiny moving thingies so that you can see Brownian motion, right? So let's say you don't sense any geometry. The geometry around you is just a uniform space where you can just diffuse in it, right? So if you diffuse in this, right, if you look at the red beads, you will basically just adopt a normal Brownian motion where you will diffuse in any places randomly at about the same speed, and your diffusion speed will not depend on where you are. You can basically diffuse freely, right? Now, let's assume a more realistic model of the nucleus, which is a volume exclusion model, where here the triangles, squares, and circles basically represent big chunks of molecules, like the chromosomes or like polymerase or like other complexes that are around it, right? Now, if you diffuse in that, if you look carefully at the red beads, you're going to see that they don't move the same way as in a uniform space. Here, what's going to happen is that they're going to start to get trapped in between those molecules and explore tiny local pockets a lot more, and so they won't be able to go anywhere, and they will actually stay longer in tiny pockets, and they won't follow a normal Brownian motion diffusion, right? So that comes to a small review on the different potential nuclear geometry, right? Either you're having a completely empty space, or you can have a volume excluded space, right? And the latest model that people believe nowadays when they look at chromatin conformation, for example, is actually a fractal space. And because I'm no magician, I cannot do a fractal space in 2D and show you beads moving around, so that's why you don't have the chance to look at it. But you'll have to believe me that the difference between an empty space and a fractal space is the way you actually move around it, right? In an empty space, you will adopt a non-compact global exploration using Brownian motion, which means that basically the probability of you going 2 times at the same place in that 3D space is less than 1. And it's actually usually very small. But for a compact exploration, which is the sort of exploration you will have in a fractal space, the probability of you to actually visit twice the same location is equal to 1. Which means that you will have redundancy. You will go over and over again to the same location, and let's say the first time you find your binding site, but you bounce on it because you were going faster, well, you actually have a second chance, right? That's what it means to have a compact local exploration. And so that leads me to the paper I'm going to talk about today, which is Single Molecule Tracking in Live Cell reveals distinct target search strategies of transcription factor in the nucleus, published by Xavier Darzak and Eli about a year ago. And in that paper, the author tried to study the sensing of the geometry of the nucleus by different molecules, right? And so in order to do that, they needed a way to record the different motion of the molecules in the cell. And to do that, they used Pal microscopy, and especially single molecule Pal microscopy. So they activated fluorophores, here is Dendra 2, which is photoactivable GFP, and then you activate it with a very low rate, so you only have one molecule at a given time in a frame, and you take a series of pictures of that with like a 10 millisecond interval, and so that gives you a movie of the molecule that like moves around the nucleus, right, in vivo. So then you use a tracking algorithm, and what you can extract is sub-diffracted position in space of that molecule moving around, and you get the trace of the path that that molecule followed, right? So now, what can I do with that data, right? So I have the trace of the molecule. So if I look at this data, there's the first parameter that I can extract is the length of each step, right? So how far did I move since the last time? So that's kind of like the speed, or here, what I'm gonna call this translocation, right? So like how much did I translocate from one point to the other? And using that, you can calculate the mean square displacement, or MSD. And so the MSD is basically something that gives you a sense on how far did I move, or how much of the available space around me did I explore. And if you have a linear normal diffusion, you will basically follow a linear relationship between the MSD and the time and the slope of that linear curve as your diffusion coefficient, which represents how fast you move, right? So the higher your diffusion coefficient, the more the slope is going to be big, and the more you're going to move fast in space. Now, imagine that you're trapped, you're confined in a small volume, right? Then your relationship of how much do I move in time will actually not be linear anymore, because you're trapped, you cannot move as much as you will normally do. So what happens is that you have what we call an anomalous diffusion, where the MSD versus time is actually going to follow a power law that's traced away from linearity, right? So that's the first parameter you can study for trying to study diffusion. The second parameter you can try to look at is the angular distribution. That is, when I move and I make steps and I'm moving around the cells, right? If you remember the beads, they bounce against each other and they change trajectories all the time, right? So if I measure the angle in between each change of trajectory that I have on my trace, then I can plot the whole distribution of this. And if I freely diffuse in space, well, I have no preferential angle at which I'm going to move, so my distribution of angle is basically going to be a round circle, which is a uniform distribution because I'm not confined, so I can diffuse in any direction. But now, if I'm actually trapped into something of a small size, then my distribution is going to be skewed toward 180-degree angle. And this is because if I go and there's a wall in front of me, I'm going to bounce and I'm going to go back, right? I'm going to go backward, which means that the angles are going to be about 180 degrees, right? And so those are the two parameters that the author are going to use to study different molecules moving around the nucleus. So first, they benchmarked their system. They looked at a completely freely diffusing molecule, which is Dendra-2, right, which has no interacting partner, and another molecule, which is H2B. So H2B, because it's bound to DNA, will actually have an anomalous diffusion because it's constrained in space, it cannot go anywhere, right? So when you look at the MSD over time, you see that H2B adopts a very nice power law, which looks like an anomalous diffusion, where it saturates really quickly, which means that it explored all of the available space around it. But for Dendra-2, you have a really nice linear relationship, which then strays away. The reason why it strays away puzzled the authors, so they decided to plot the translocation histogram. And that is basically the frequency at which you make move of 0.5 micrometer, 1 micrometer, etc., etc. And so they tried to fit that histogram with a normal diffusive population. And it doesn't work. As you can see here with the dashed lines, it doesn't fit the data really well. And for two population, it fits it a little bit better, but actually, in order to have a really good fit of the data, they needed to use 3 population. And what that means is that Dendra-2, when you look at the trace, you will actually see that there is fixed Dendra-2 that do not move, right? They just jiggle in space. Fast diffusing one, which make very big jumps and translocation steps, and slowly diffusive one, which have tinier translocation steps, right? And the reason why the linearity strays away here is what the author called a population exclusion effect, which means that the fast diffusing population will actually go out of the field of view of the microscope. So you're losing it. So that the data that is represented on the layer time point actually lacks one of the 3 populations of Dendra-2 they found. And this is why this strays away from the linearity that you have at the beginning, because here you only representing a partial set of data, right? So now that the author had a way to study and they benchmarked it and it works and they can see that they can detect anomalous diffusion from normal diffusion, they went on and they decided to study two transcription factors, CMYC and PTFB. So CMYC is a transcription factor that binds to about 36,000 target sites on the human genome and it acts as a global enhancer of transcription. PTFB is a kinase that binds to polymerase II, CTD and complex and activates transcription. Thus, it has to search and bind to also a lot of active sites on the genome, which are also very numerous, right? So the interesting thing here is that both proteins have target sites throughout the whole genome, which means that they will probably adopt very similar strategy, or so that's what you can think. But when you measure the diffusion of those molecules, you can actually see that for CMYC, you have an MSD over time, which is kind of linear and strays away from linearity, right? And when the author looked at it, they also found three populations, a fast diffusing one, a slowly diffusing one, and a fixed one. So they explained that straying away from linearity with the same population exclusion. But for PTFB, what was interesting is that they actually have only one population in here, and so the bias that you can see on the curve here and the fact that it's not linear is actually representing an anomalous diffusion. And so in order to study a bit more of the geometry that those molecules were sensing, the author then decided to look at the angular distribution because as I've explained, if you have walls around you, you're going to bounce back, and so this measure is actually going to give you a sense of what geometry are the molecules sensing. And so when you look at Dendra2 and H2B, you have the sort of textbook example where Dendra2 has a really nice, strong, uniform distribution, where H2B is very skewed toward the 180 angles, right? And CMYC, because it's freely diffusing, also adopts a nice round distribution, and PTFB, because it's anomalous, also adopts a 180-degree bias, right? And so now the author wanted to go a bit further and try to study the dependency of that movement, right? The dependency on how much do you actually bounce back through time and space. So what they did is that they find a measure that they call the asymmetry coefficient. And this is the log of the forward movement over the backward movement. So when you have an asymmetry coefficient of 0, it means you have a uniform distribution. But if you have an asymmetry coefficient that strays towards the negative value, it means that you actually move a lot more backward than you will move forward because you're taking the log of a value that is less than 1, so you're becoming negative. And so when you look at CMYC, you find that it has a very interesting characteristic where it slowly becomes more backward. So the longer you look at the molecule, the more backward the chance of the movement of CMYC has a higher chance of actually becoming backward. And when you look at the spatial dependency on the movement, you can see that at low translocation step, CMYC actually adopts a backward motion, but at high translocation step, CMYC has no asymmetry coefficient, which means that it's pretty much uniform. And the second very interesting thing here is that for PTFB, you have an invariance through time and an invariance through space. That is, whatever time I look at PTFB or whatever space PTFB is exploring, it doesn't seem to change the way it's bouncing back. So it doesn't seem to change the way it's perceiving the wall around itself, whatever size it's trapped in, which is very interesting. And so in order to understand a bit better what may comes on here, the author then decided to do some numerical simulation. So for CMYC, they tried a different number of models, and the one that they found that worked really well was a slow diffusion trap model. So if you're CMYC and you're just diffusing in space, you have a probability of entering an area which is of small size, and within that area you're going to bounce back and slowly diffuse. Then you're going to exit it and go back onto like a normal freely diffusing molecule. And this recapitulates pretty well the uniform distribution you find for CMYC of angular distribution, and it also recapitulates really well the asymmetry coefficient that decreases over time. And if you think about it, it's because the longer I wait and the longer I look at CMYC, right, the higher the chance of CMYC to enter a trap is, right? So the longer I wait, and the longer I wait, the more my population of CMYC is actually going to skew backward in angle because a lot of them will have entered traps, right? This is why you have that slowly decreasing AC. And the dependence on space, of course, follows also the nice thing that they found for CMYC, which is at low translocation step, you have backward angle, but at high one, you don't. And this is because once you're in the trap, right, you basically bounce back, but the trap has a fixed size, so you cannot make bigger steps than this. So this is why the small translocation step is biased toward backward angle. Then they went and looked at PTFB. And so for PTFB, if you remember, there was an invariance through time and space. And what an invariance through time and space means is usually that the space around you is a fractal space, because that is exactly the definition of a fractal. That is, the statistical measurement you will do of the object does not change whatever zoom level I'm looking at it, right? So here, they tried some numerical simulation with 3 different fractal spaces. One which is a power law trap model. So it's the same as the trap model from before, but the trap size is basically power law distributed, which gives it a fractal space. Another one is a percolation cluster, which is a geometry-less fractal, which still has invariant statistical property. And the last one is a Sierpinski carpet, which has a conserved geometry and conserved statistical invariance through space. And so when they look at this, they actually found that the angular distribution recapitulates pretty well the 180 backward motion that they find. And when they look at the dependence on the asymmetry coefficient through time, they have a very nice invariance for all of those models. But when it becomes kind of interesting and it starts to fall apart a little bit is when they look at the space dependency of the asymmetry coefficient. So for a parallel trap model, you have a weird V shape here, which is not invariant, so it doesn't work. For the percolation cluster, your space dependency decreases over a translocation step, which also does not work because it's not invariant anymore. But for the Sierpinski carpet, you actually have a really nice, invariant asymmetry coefficient. But the problem with the Sierpinski carpet is that if you remember on the data that I showed you, right, we had a very nice backward skewed motion, but the Sierpinski carpet only has a very slight, if not zero, it's debatable, backward motion. So that the Sierpinski carpet, even if it does recapitulate the invariance, does not really recapitulate how much the molecule goes back. So what does it all mean, right? For a transcription factor to actually sense those different sort of geometry. Well, if you remember at the beginning, I told to you about the non-compact versus compact search, right? And because PTFB senses its environment as a fractal space, it will adopt a compact search mechanism. So that the way it will find its target is going to be very different from CMYC, which then is a freely diffusing molecule, right? And that brings me to my conclusion, which is that the data here in this paper is really nice and really well collected, and it shows 2 different perceptions of the geometry, leading to 2 different search strategies, compact and non-compact. And that is very interesting because, as I said at the beginning, CMYC and PTFB binds pretty much through the whole genome, so why would one adopt a different strategy and a different search mechanism? But the numerical simulation that they've done show that the mixed trap model somehow recapitulates CMYC pretty well, but the fractal model only partially explains PTFB. And this is one of the big downfalls of this paper, is that they actually did not succeed in finding an actual model that explains why PTFB moves in that way. And this leads me to the future direction, which is to assess what makes you sense different geometry, right? What in PTFB and in CMYC, what of the protein actually makes them sense the geometry? Why do they sense geometry in, the first time? Why are you trapped when you sense a fractal space? Or why do you not sense it? Those questions, they don't answer at all. But also a better understanding of the underlying geometry. Because as I showed you, the fractal model they've tried don't actually recapitulate really well the data. And so if we were to understand better how the nucleus geometry is organized and how the molecules are organized in the nucleus, then we will be able to better model PTFB in those better fractal model space, right? And finally, also measure more proteins, try to look at other transcription factor. Is that a very represented thing that they sense different geometry? Or all of them are mainly freely diffusing and only PTFB has that property? We don't know because they only measure 2. And one last thing is kind of a wild card, but what about the cytoplasm, right? Because cytoplasm has a lot of cytoskeleton elements and everything. So how do you sense geometry in the cytoplasm? Is also a very interesting question that I think will be interesting to look at. And so on that, I would like to thank my 2 coaches, Florian Enger, and Dan Needleman. Yes, Andrew?
Yeah, so when they track the molecular, how does they know this molecular is diffusing in the nucleus but not sliding in the DNA?
How do they know? They don't.
They don't?
They don't, like, what do you mean?
Yeah, I mean, there are two probabilities. That one is the transcription factor is sliding on the
Yeah.
The other is they diffuse in the nucleus.
Yeah.
But they two must have different kinetics. So.
Yes, oh, you mean like for the 1D, 3D search model?
Yeah.
How do they do that? Oh, so there's been study where they actually look at like in vitro, mainly most of the studies are actually made in vitro, where they put transcription factor and molecules of DNA on a slide, and they look at the diffusion of the transcription factor, and they can see that it diffuses in space, and eventually binds to the DNA, slides on it, and jumps back. They've actually even measured it. It's like about 150 base pair. Usually that the transcription slides before it jumps, at least for bacterial DNA, like the lag precursor and the lag operand. In that sense, that's how they've measured it. Andrew?
So they started out by measuring a molecule which they expected to just show regular diffusion.
Mm-hmm.
And then it didn't, and they tried to wiggle. But what's the explanation for why there are these different populations for a small molecule?
Oh, for the three different populations for the small molecule?
Yeah, I mean, what's going on? I mean, supposedly this is a small molecule that can go everywhere. It's not supposed to show anomalous diffusion, and so some people would have stopped the experiment there, right? Like, the control doesn't work, I quit.
Yeah.
We're assuming that running into the side of the nucleus, right? You get anomalous diffusion.
Yeah, exactly. You will, yeah, but because they're looking at a very small subset of the space of the nucleus, they're not supposed to run on the side, theoretically, right? But for that, they actually, like, the author don't provide any explanation of those three populations. They literally just like very rapidly on that, and be like, oh yeah, we have, like, when we feed the data, we can see that there's three populations. This is gorgeous. My own take on it when I was trying to think about that was that probably some of those molecules, at least for the slow diffusion versus the fast diffusion, like the nucleus is a very complex environment, and there is a lot of different cloning which differ, right? It's more condensed or less condensed for the DNA. So maybe if you diffuse in those different space, this is why you have different like slow and fast population. For the fixed one, the like dendrite that doesn't move, that one I actually don't get it. Like maybe it gets trapped somewhere, but like I'm not sure I understand why it will get trapped.
I want to ask a question about this. So you have three populations. One is freely diffusing, which is the square displacement will be proportional to T.
Mm-hmm.
And then you have two more trapped populations, which their square displacement will be not proportional, but actually smaller than T. And you sum those up, and somehow you get T. Proportional to T. Can you explain that to me? That doesn't make the math doesn't add up.
Yeah. So I looked it up too, and so it like. They do some like numerical simulation for that. They don't actually look at the math behind it. What they did is that they tried to simulate a three population of like one molecule that has three populations. One which is fixed, one which is slowly diffused, not trapped. It's only slowly diffusing, right?
Yeah.
There's
but
no.
Still, it will be like skewed.
It wouldn't be skewed. The slope of the it's just that the slope will be different, right? But if you slowly diffuse or you diffuse fast, if only your diffusion coefficient changes, right? You still have a linear relationship.
You still have two linear populations.
Mm-hmm.
One is that is not linear. And
Yeah.
then you add them up. How do you
like,
get?
you know, if you have basically if you have the slow diffusing population and the fast diffusing population, right? And you add them up, right? You will have something
But
which like
there is
average.
an extra population that is not linear, right?
Well,
And
exactly.
those are-
But that
and
extra
that's linear.
population, basically the way they cope with it is that the extra population does not represent a lot of the data. It's only a very, very small subset of the
But you
data.
said it's because you're losing
Yes. So the
some
reason,
population so that it's not linear.
yeah. So when you look at the data, actually what happens is that you have like the data point is that. So you actually have one linear here and one linear here.
Oh,
right?
I see what you mean.
This is it, and so like this is why it strays away, but it doesn't adopt a power law. It actually adopts another linear
Oh, I see.
thing, right?
And another question here. So I doubt your explanation regarding the why the skewness coefficient, what is it called, skewness coefficient, like the population that is going forward versus the population.
Oh, the asymmetry coefficient.
Yeah, asymmetry coefficient, why it goes down over time. And
Yeah.
in one of those projects, I think it's not.
Simic? Yeah.
Yeah, I don't think your explanation makes sense because you're actually measuring a steady state population, right? So whichever time point you look at should all be the same. I think what explains this drop of asymmetry coefficient is that you lose basically all those like fast, freely diffusing molecules go out of your like field of view, and you are left with those that are trapped. So that basically you have, if you have enough sample, you should always see a flat line. But as time goes by, you lose all those that are like freely diffusing, and you only keep those that are trapped, so that you get this kind of downward slope.
It's like I don't disagree with you. The way the author looked at it in the numerical simulation, and the reason they claim is because of
I think if you, in this case, if you assume that there is only one molecule and it starts from a freely diffusing state, then your explanation works. But if you are looking at a huge population of molecules, some of them are freely diffusing and some of them are already trapped, then averaging that up, and you let the system relax until to some kind of steady state, then it shouldn't be any different if you look at different time points.
Yeah, no, I mean, I don't disagree with you on the population thing. Do in their, like, at least for, like, their model of the numerical simulation data that explains it, right? That's the explanation they came up with, was that, like, as you look more in time, a bigger proportion of the population is actually going to get trapped. And maybe if you were to look at longer time point, then you will arrive at that, like, steady state where you have a flat line of, whatever proportion of your molecule is actually trapped, the other is not. But the decrease that they see here, they account for more and more molecules get trapped over time. But I don't disagree with you with what you're saying. That it's kind of a flimsy
It
explanation.
doesn't make, if you're looking at a very, sorry.
Next question.
Quick one. Do we know anything about how these molecules differ in size or charge or complex formation? It's clear that in principle, the same environment, they just need different geometry, and that kind of physical difference is sort of really obvious.
Yeah, so their size is about the same. The way they bind is very different. So the TFB binds to the CTD of the pole 2, which has a lot of sites. So it has about 150 binding sites on that CTD. So that it can bind in a lot of different locations. But for CMYC, it actually looks for like an 8-mer cassette on the DNA. So the way they bind is very different, and maybe that has an impact on how they diffuse. Also, PTFB isn't known to necessarily interact with the DNA. It's known to interact with stuff like C7SK, the non-coding RNA. So it has a lot of other interactor. Well, CMYC has no known really interactor and just binds to the DNA. So there's those all other interaction in the cell that probably are the reason why this perception of the geometry